All right, my friends, here we are at the final step of this implementation, and actually the most exciting one, because this is the step where we're going to visualize on a nice 2D plot the prediction curve and the prediction regions of the logistic regression model. All right, so more specifically, what we're about to plot is a two-dimensional plot with therefore two axes, x and y. On the x-axis, you will have the first feature corresponding to the age, and on the y-axis you'll have the second feature corresponding to the estimated salary. And therefore, each of the points, each of the observation points you will see on the 2D plot will correspond to a specific customer. It will either be a customer of the training set, on the plot of the training set results, or a customer of the test set on the plot of the test set results. And what is most interesting to see in this plot will be the prediction regions, meaning the regions where our logistic regression model predicts the class 0, meaning the customers didn't buy the SUV, and the other region where our logistic regression model predicts the class 1, meaning the customer bought the SUV. And lastly, what will be really interesting to see is the curve separating these two regions, the region of the prediction 0 and the region of the predictions 1. And this is exactly how we're going to see the difference between linear classifiers and non-linear classifiers. So here we're only starting with one classification model, logistic regression, so we won't compare that yet, but you will see in the next sections of this part that the prediction boundary, we call this the prediction boundary between these two prediction regions will be different depending on whether or not your classifier is linear. All right, so I can't wait to show you this, and let's start first by visualizing these training set and test set results for the logistic regression model. All right, so the code to visualize this is actually pretty advanced. And not only it is pretty advanced, but also you will probably never use it again in your career, or let's say you will never have to implement that again. Why is that? It's because in your career you will mostly work with data sets having many features, more than two. And here the only reason why we have a data set of two features is so that we can be able to visualize indeed, these prediction regions and prediction boundary, because indeed in order to visualize this, we need maximum two features, because one feature corresponds to one dimension in this plot. So the code to visualize these results is only useful for training purposes, and it will not be useful for your future machine learning career. So what I suggest is that we don't waste too much time, understanding the whole code and re-implement it ourselves, because really I'm going to show it to you right away, on the original logistic regression implementation. You will see that the code is pretty advanced. It's not like plotting a regression curve like we did in part 2. So that's the test set results. Let me show you the training set results. All right, so that's the code. You see, it uses a lot of tricks to plot all these observation points, prediction regions, and prediction boundary. So if you want to have a look at it and understand it, fine, but really for the others, it's totally okay if we don't cover this code in detail, because this is only for training purposes, just so that I can show you the differences between linear classifiers and nonlinear classifiers, and you will probably never use that again in your future machine learning project. However, what I will do just now is explain how it's done. Basically, what we do is we create, as you can see, a grid, which is basically this frame here containing all the ages of your features and all the estimated salaries, the ranges, and you create this grid with a high density, meaning that the pixels of this grid are not separated one by one, but every 0.25. So here, for example, for the age, it goes this way. It goes from 10 to 10.25 to 10.5 to 10.75 to 11, etc. up to 69, 69.25, 69.5, 69.75, 70. Okay, and same for the estimated salary. It goes from 20,000, then 20,000.25, 20,000.5, etc. up to somewhere around 149,000, 149,000.25. You see, so resulting in having super dense points inside this grid. And then the trick, what we did is not only we plotted all the real observation points in the grid, so all the points that you see here are the customers of either your training set and then later on your test set. The green points are of course the customers who bought the SUV, represented by 1 here. And the red points are of course the customers who didn't buy the SUV, represented by 0 here, okay? So all the points are your observation points, your customers. And then, so the trick, in order to plot the prediction regions and therefore that prediction boundary here, separating the 2 regions, is to apply the predict method onto each of these dense points in the grid. So that all the dense points here, in this region, were actually predicted to be 0, meaning all the customers, other customers inside this region are predicted not to buy the SUV, and all the observation points in this green region are actually predicted to buy the SUV, because the region here is green, representing the predictions of 1. And all the red points here, this red region, are all the observation points predicted as 0, meaning all the customers who were predicted not to buy the SUV. So you see how this works? That's the trick. And then really you don't have to understand all the techniques used to implement this, because once again, you will probably never have to implement that kind of code in your career. All right? So what we're going to do now is we're going to get that whole code, from the original file. We're going to paste it inside our new implementation. There we go. And we're going to do the same for the test set. And then I will actually try not to show you the test set now, but let's get the code. Let's paste that below in a new code cell. And now let's enjoy the results. So what we're going to do is first execute this cell. It's going to take a little while actually, because the step is 0.25, meaning we will get a very, very dense grid, as I've just explained. And therefore, the predict method is applied on each of these dense points of the grid. And that's why there are actually a lot of predictions to compute. And that's why it's taking a little time. But there you go, it's coming. Here we go. So not that long, that's good. We just got the results of the training set. Let's also plot now the results of the test set, and then I will make my comments on the results. All right, so we can just let it run and start by observing and interpreting the results of the training set. All right, so just to recap, you have to understand 4 things in this plot, is that all the points that you see here, whether they're red or green, are the real customers and their real results in the training set. The green points correspond, of course, to the customers who bought the previous SUVs, and the red points correspond, of course, to the customers who didn't buy any previous SUV. And then the other 2 things to understand is that those colored regions here, this red region and the green region, are the prediction regions. So this region is the region where our model predicts that the customer didn't buy the SUV, and this region is the region where our logistic regression model predicts that the customers bought the previous SUV. And so, in order to figure out where the correct predictions are and the incorrect predictions are, well, the correct predictions are where we have some observation points with the same color as the prediction region, and the incorrect predictions are where we have some observation points with a color that is different than the prediction regions. For example, this customer here, who in reality bought the SUV, corresponding to 1 here, is actually an incorrect prediction because it falls into the wrong region, the red region. And vice versa, this customer here, who in reality didn't buy the SUV because it corresponds to 0, well, it's a wrong prediction because it falls into the green region where customers are predicted to buy the SUV. And then finally, what's the most interesting in all this is the prediction boundary. As you understood, the prediction boundary is the boundary between those 2 prediction regions, the green prediction region and the red prediction region. It is where your classifier separates basically the 2 classes, the class 1 and the class 0. And now you have to understand something very, very important. It is the fact, it is the observation that the prediction curve of the logistic regression model is actually a straight line for one specific reason. It is because the logistic regression model is a linear classifier. For any linear classifier, the prediction boundary or the prediction curve will always be a straight line, in 2 dimensions. In 3 dimensions, it will be a straight plan, okay? So that's what we get for linear classifiers. And what will be really interesting to see in the next sections, when building other classification models, is that indeed for the non-linear models, like for example, naive Bayes or kernel SVM with a nonlinear kernel, well, you will see that the prediction curve or the prediction boundary will actually not be a straight line. And I won't reveal now what it will be, but we will see. It will be fantastic to observe. All right, so now you understand it better, but remember that these are the training set results. Therefore, all these customers that we see here are actually in the training set. Therefore, these are customers with which our logistic regression model was trained. And therefore, that's kind of easy to provide such results because these are exactly the observations of the training. But now what we would like to see is how our logistic regression model was able to perform on new observations, meaning on the observations of the test set, the customers of the test set. Because indeed, the customers of the test set are new customers with which our logistic regression model wasn't trained. And so we have to see if our logistic regression model was still able to separate well the 2 classes, meaning the customers who bought the SUV and the customers who didn't buy the SUV, even despite the fact that these are new customers on which the model wasn't trained. And that's exactly what we're about to see now when visualizing the test set results. We already executed the cell here, and so these are the test set results. And still, our logistic regression model was perfectly able to separate well the 2 classes, 0, all those red points here, and 1, all those green points. There are still some incorrect predictions, of course, like this customer who in reality didn't buy the brand new beautiful SUV, but was predicted to buy it, and a few incorrect predictions here of the other class, meaning these customers who in reality bought the SUV, but were predicted not to because they fall in the red region. All right, and so how can we conclude here? What should we conclude, and what are the takeaways we should get for our future classification models? Well, first, the logistic regression model does a very good job at separating our 2 classes and therefore at predicting whether the customers bought the SUV, but we actually would hope to build a model that has less prediction errors. And how can we build one? What would we need to get, as the prediction curve in order not to predict incorrectly all these wrong predictions here, all these customers here? Well, we actually would need a prediction boundary that is something else than a straight line. Because even if you try to rotate your prediction line, for example, to be like that, well, it will still catch many incorrect predictions. So what we would need to get, optimally, is some kind of curve, some kind of prediction curve that goes this way, catches all the red points, all the red customers here, and then go around like this in order to catch all the red points, the red customers, and leave all the green points, the green customers, inside the green region. And well, as you might guess, this is what we might be able to get with nonlinear classifiers. I won't tell you more now, but be ready for some even more performant classification models that manage to separate even better these 2 classes. All right, so that was the teaser for the next sections, and now I hope you enjoyed this implementation of the logistic regression model. Congratulations, because that was a long one. However, after this big amount of effort, we'll actually collect some nice fruit, because guess what? The implementation we did here for the logistic regression model will work for all our other classification models. And by that, what do I mean? Well, I mean that the implementation we did here is actually a very good code template. It is a code template for classification. Because indeed, in order to implement the other classification models, we will only have to change one single cell of this implementation, which is of course the cell where we build and train the classification model. We will only have to change this cell where we build a classifier and train it on the training set. And all the rest will be the same. We won't have to change anything here because we will just call our classifier to predict this single result and then all the results in the test set. And same for the visualization. We won't have to change anything, except the name of the model here, because indeed all the variable names will be the same. You know, the classifier, which here is the logistic regression model, but in the next sections will be the other classification models. And then of course we have the same variable names for the training set and test set. And so that's why we won't have anything to change in our future implementations of the classification models, except the part where indeed we build and train our classification model. So we will be extremely efficient in our future implementations of the classification models because we will only have to recode that cell here, and that's it. We will just re-implement this, to implement the right classification model, and then we will do a run all to enjoy at the end the final results, the new prediction regions, and especially the ones for the nonlinear model where we are hoping to get a regression curve that goes like this in order to catch the maximum right predictions. All right. So there we go. That was the big part of the job. You did it. And now follow me in the next sections to implement the other classification models. And until then, enjoy machine learning.